Space is vast, filled with wonders. The universe stretches out infinitely, a canvas of stars, planets, and galaxies. Each point of light in the night sky represents a distant world, a potential mystery, waiting to be unraveled. Among these celestial wonders, one of the most intriguing and enigmatic phenomena is the black hole. Black holes are among the most fascinating. These cosmic giants captivate our imagination and challenge our understanding of physics. They are regions in space where the gravitational pull is so intense that nothing, not even light, can escape their grasp. This makes them invisible to the naked eye, detectable only through their interaction with surrounding matter and the effects they have on their environment. Imagine a place where gravity is so strong, nothing escapes, not even light. This is the defining characteristic of a black hole. The boundary surrounding a black hole is called the event horizon. Once something crosses this boundary, it is lost forever, the black hole's immense gravitational pull. The concept of an event horizon is crucial to understanding the nature of black holes. That is a black hole, a cosmic abyss, a place where the known laws of physics break down and our understanding of space and time is stretched to its limits. The very fabric of space-time is warped and twisted by the black hole's gravity, creating a region of infinite density known as a singularity at its core. Black holes are not empty holes. They are incredibly dense objects with immense gravity. The matter that falls into a black hole is compressed into an incredibly small space, increasing its density to unimaginable levels. This process releases a tremendous amount of energy, often seen as bright jets of radiation emitted from the area around the black hole. They are incredibly dense objects with immense gravity. The gravitational pull of a black hole is so strong that it can capture stars, planets, and even light. This immense gravity also causes time to slow down near the event horizon, a phenomenon predicted by Einstein's theory of general relativity. They warp space and time around them. This warping effect is so powerful that it can bend light, creating a visual phenomenon known as gravitational lensing. This effect allows astronomers to detect black holes by observing the way they distort the light from stars and galaxies behind them. Think of a star, much bigger than our sun. These massive stars live out their lives burning through their nuclear fuel. When they exhaust their fuel, they undergo a dramatic transformation. When it runs out of fuel, it collapses under its own gravity. This collapse triggers a supernova explosion, one of the most powerful events in the universe. The outer layers of the star are blasted into space, while the core collapses into an incredibly dense object. This collapse creates a black hole. The core's gravity becomes so strong that it forms a singularity, a point of infinite density. The black hole then continues to grow by pulling in surrounding matter, becoming a cosmic abyss that shapes the universe around it. Stars are giant balls of hot gas. They shine brightly, powered by nuclear fusion. But even stars have a lifespan. Massive stars, much bigger than our sun, eventually run out of fuel. When this happens, gravity takes over. The star's core collapses in on itself, creating a supernova explosion. This explosion is so powerful it can outshine entire galaxies. The remaining core is compressed into an incredibly dense point, a black hole. Imagine approaching a black hole. As you get closer, gravity gets stronger. Eventually, you reach a point of no return. This is called the event horizon. At the event horizon, gravity is so strong that not even light can escape. Once you cross the event horizon, there's no going back. The event horizon is not a physical boundary. It's a region in space-time where gravity becomes inescapable. Black holes are not just cosmic oddities, they play a crucial role in the evolution of galaxies. At the center of most galaxies, including our own Milky Way, lies a supermassive black hole. These black holes are millions or even billions of times the mass of our sun. Supermassive black holes influence the formation of stars and the motion of gas and stars within galaxies. They shape the universe as we know it. Section 5. Spaghettification, stretching to the limit. What would happen if you fell into a black hole? It's a question that has captured the imagination of scientists and science fiction writers alike. As you approach a black hole, the difference in gravity between your head and your feet would become extreme. This is called tidal force. You would be stretched out like spaghetti, a process aptly named spaghettification. It's not a pleasant way to go. Section 6. Hawking radiation, black holes. Not so black? Black holes are often depicted as inescapable voids. But in the 1970s, physicist Stephen Hawking proposed a revolutionary idea. Hawking suggested that black holes are not entirely black. Instead, they emit a faint radiation due to quantum effects near the event horizon. This radiation, known as Hawking radiation, causes black holes to slowly lose mass over time. Hawking radiation is incredibly faint and has not yet been directly observed. Section 7. Time warps, relativity's playground. Black holes are not just about extreme gravity. These cosmic giants are fascinating for many reasons, one of which is their ability to manipulate the very fabric of space-time. Imagine a place where the rules of physics as we know them are pushed to their limits. Black holes are regions in space where the gravitational pull is so strong that nothing, not even light, can escape from them. This immense gravity is due to a large amount of mass being concentrated in a very small area. They also warp time itself, as predicted by Einstein's theory of general relativity. According to this theory, massive objects cause a distortion in space-time, which we perceive as gravity. The more massive the object, the more it warps the space-time around it. In the case of black holes, this warping is so extreme that it creates a sort of well in space-time. This well is so deep that it affects the flow of time itself. Time slows down as you approach a black hole. This phenomenon is known as time dilation. The closer you get to the event horizon, the point beyond which nothing can escape, the more pronounced this effect becomes. If you were to hover just outside the event horizon, you would experience time at a much slower rate compared to someone far away from the black hole. Someone watching you from a safe distance would see your clock ticking slower and slower. To them, it would appear as though you are moving in slow motion. This is because the intense gravitational field of the black hole stretches time. The closer you get to the event horizon, the slower your clock ticks relative to an observer who is far away. If you could survive a trip to a black hole and return, you would have aged less than those who stayed behind. This is a direct consequence of time dilation. While you might experience only a few hours or days, years could have passed for those on Earth. This concept is not just theoretical. It has been confirmed by experiments involving precise atomic clocks on airplanes and satellites. It's time travel, at least in theory. The idea that you could travel to a black hole and come back to find that you have aged less than everyone else is a fascinating implication of general relativity. While we are far from making such journeys, understanding these concepts helps us grasp the incredible nature of our universe. Black holes are not just mysterious objects. They are gateways to understanding the fundamental laws that govern time and space. Section 8. Mysteries of the Singularity. At the very center of a black hole lies a point of infinite density called the singularity. Here, our current understanding of physics breaks down. What happens at the singularity? Do the laws of physics as we know them still apply? These are questions that continue to baffle scientists. The singularity remains one of the greatest mysteries of the universe. Section 9. Conclusion. The allure of the unknown. Black holes are objects of both terror and fascination. These enigmatic entities captivate our imagination and challenge our understanding of the cosmos. They are regions in space where gravity is so strong that nothing, not even light, can escape their pull. This makes them invisible to the naked eye, detectable only through their interaction with surrounding matter and the effects of their immense gravitational fields. They represent the extreme limits of gravity and our understanding of the universe. The study of black holes has led to groundbreaking discoveries in physics and astronomy. For instance, the detection of gravitational waves, ripples in space-time caused by the collision of black holes, has opened a new window into the universe, allowing us to observe cosmic events that were previously beyond our reach. While we have learned much about black holes, they continue to hold many secrets. The event horizon, the boundary beyond which nothing can escape, remains one of the most mysterious aspects of black holes. What happens to matter and information that crosses this threshold? This question has puzzled scientists for decades and continues to be a topic of intense research and debate. Their study pushes the boundaries of our knowledge and inspires us to explore the cosmos. The quest to understand black holes drives technological advancements and fuels our desire to venture into the unknown. From the development of more powerful telescopes to the planning of ambitious space missions, the pursuit of black hole research is a testament to human curiosity and ingenuity. The universe is full of wonders. Beyond black holes, there are countless other phenomena that intrigue and inspire us. Nebulae, the birthplaces of stars and galaxies, vast collections of stars, gas and dust, each hold their own mysteries. The more we learn about the universe, the more we realize how much there is still to discover. Black holes are a reminder that there is still so much out there to discover. They symbolize the unknown, the uncharted territories of our universe. As we continue to study these cosmic enigmas, we are reminded of the boundless possibilities that lie ahead. The allure of the unknown drives us to keep exploring, to keep questioning, and to keep pushing the limits of our understanding.